Dear students, good morning. Again, I welcome you in this online class. In a series of lectures, we have already discussed the development of nucleus and properties of nuclei, and in continuation today I am going to discuss the important topic, that is the general nature and properties of the forces between nucleons. Since nuclei contain charged particles, that is protons, the forces acting between the protons should be forces of repulsion. If there were no other forces acting between the particles of nuclei, the latter would not be able to retain a stable state, because the repelling protons would fly out in all directions, and in this way nucleus becomes unstable. To have a stable state of a nucleus, we have to assume that some other forces act on the protons, which combine all the protons in the nucleus so that this nucleus may be stable. These attractive forces exceed the forces of repulsion. Even aside from the sign of the force, electrostatic forces are too much weak to account for the main effects. Again, gravitational forces are weaker still and offer no assistance in this problem. It is therefore necessary to postulate an entirely new type of interaction known as nuclear force. We can enumerate the following properties of nuclear force on the basis of various observations, empirical facts, and the study of various complex nuclei. Number 1. Nuclear force is always attractive. The force between two neutrons, two protons, or neutrons and protons, nuclear force is always attractive. Existence of neutrons and protons in a bound state is itself an evidence of this property. As you know, the nuclear force is strongest force, as this is 100 times stronger than electrostatic force and about 10 raised power 38 times stronger than gravitational force. And in this way you can say the strongest force in nature is nuclear force. Number 2. Nuclear force is short-ranged. The nuclear force is most effective up to a distance of the order of 10 raised power minus 15 meter. And as you know, this is the size of, this is of the order of the size of the nuclear radius, and decreases rapidly as the distance between nucleons increases and becomes almost negligible when separation between nucleons is of the order of 10 Fermi. The effective range up to which the nuclear force is effective is known as nuclear range. If nuclear force is not short range, then all the nucleons in different nuclei will coalesce into one big nucleus, and everything will probably turn into a huge nucleus like a super neutron star, and there will be no more a variety of elements in nature. Number 3. Nuclear force is very strong. This is evident from the large binding energy of the nuclei. As you know, it is about 8 MeV per nucleon. The average binding energy of electrons in atoms is in the range of electron volt to kilo electron volt only, and in this way you can say that nuclear force is very strong because more energy is required to bind the nucleus, or to have all nucleons in a very small space. Number 4. Saturation property of nuclear force. This is actually an outcome of the short range nature of the nuclear force. We know that the nuclei have the same density because the radius of almost all nuclei varies from r equals to r0 a raised power 1 by 3, and the binding energy per nucleon for nuclei with a greater than 40 is almost constant. These facts imply that the nuclear force saturates. Each nucleon in a nucleus interacts with its neighbors only. Also, nucleons attracts each other strongly only if they are in the same orbital state. According to the Pauli principle, only 2 neutrons and 2 protons will be found in the same orbital state. Therefore, it is possible to find 4 nucleons strongly bound or alpha particle structure, also confirmed by binding energy curve. Number 5. Nuclear force is charge symmetric. It is same, this nuclear force is same for proton-proton, neutron-neutron and proton-neutron pair. As an example, the following evidence is for a charge symmetry situation. We can consider this example here. two nuclei are hydrogen 3 and helium 3. Hydrogen 3 contains one proton and two neutrons, while helium 3 contains two protons and one neutron. So in hydrogen 3 there are two pn pairs and one nn pair, while in helium 3 there are two pn pair and one pp pair. And the observed fact is that the binding energy for hydrogen 3 is at 0.48 MeV, while the binding energy for helium 3 is almost same, that is 7.71 MeV. So the difference between two binding energy is very small, that is about 0.77 MeV. And from this observation we can say that this nuclear force is charge symmetric. Number 6. Nuclear force is charge independent. We know that the atomic mass number A is approximately equal to twice the atomic number Z for the light and intermediate nuclei. It shows that light nuclei prefer to add nucleons in neutron-proton pairs, or we can say that there is a strong interaction between neutrons and protons. The excess neutrons is in heavy nuclei confirms that neutron-neutron force is attractive, but it is sufficiently attractive to lead to a stable dineutron. For a good approximation, we can say that the forces acting between neutron-neutron, proton-proton and neutron-proton is almost equal. And as this force is almost equal between NP and NP, from this observation one can say that the forces is charge independent. Number 7. Nuclear force is spin dependent. The nuclear force depends on the spin of interacting nucleons, and this can be observed from deuterons. Number 8. The non-central force or tensor force. This is also an important property of nuclear force, that nuclear force is a non-central force or a tensor force. Nuclear force don't obey inverse square law, and as you know, Coulomb force, centrifugal force, gravitational forces all are of the nature of inverse square law, but nuclear force doesn't obey this inverse square law. Nuclear force depends on the direction of spin of nucleons, as we have already considered it a spin dependent force, which is we have already discussed, that is the seventh point of the property of this nuclear force. Nuclear force depends on the direction of spin of nucleons as we have already considered it a spin dependent force. Such spin dependent forces are known as tensor forces, having the same form as the interaction between magnetic dipoles. It is introduced to account for the observed values of the magnetic dipole moment and electric quadrupole moment of the deuterons. As you know, deuterons are having quadrupole moment as well as magnetic dipole moments, and these observation facts can only be explained if we assume that the forces between nucleons is of the type of is of the tensor nature. So we use the principles of the wave mechanics on nuclear problems, and then by comparison with experimental data we find a consistent description of the nuclear forces acting between two nucleons, that is, two body problems. Therefore, there are two general methods of investigation: the study of neutron proton and proton proton scattering events over a wide range of energy, and the study of deuteron, which is a bound state of two nucleons. And that's all in today's online lecture. Thank you.